In this chapter, in this section, we're going to show how we change from one coordinate system to another coordinate system, how we transform the velocities. And this is fairly straightforward, but what we'll see is, unlike when we're transforming coordinates, we're transforming spatial coordinates, where y and z are unaffected, obviously because velocity is the rate at which we change spatially with respect to time. Any change in the time is going to affect our y and z velocities, our perpendicular velocities to the direction that the frame of reference is traveling. So let's start and see how we get our different velocities, and then we'll do some applications. So once again, thinking about how this works, if we're doing a Lorentz transform, typically we have one frame of reference and then we have a second frame of reference, this prime frame of reference, which is moving at some velocity with respect to this. Now, let's say in this frame of reference, I have some object, maybe a spaceship, traveling a speed of u. Now, notice I've switched from v to u. I'm using u for the velocity of an object because v is usually used for the velocity of the frame of reference with respect to another frame. So here's what's happening. In S prime, okay, the ship is moving at u prime, okay, meters per second. In frame S prime, its velocity, or I should say, the frame S prime is moving with some velocity v with respect to our frame S. So the problem is I want to convert this velocity in one frame to another velocity in a different frame. Okay, how do I do that? Well, it's not so simple as you might think. You might say, okay, well, just take my change in x over change in time, and I can get that. My y and z velocities won't change. No. Remember, time is different. Time flows at a different rate with respect to one another in the different frames. So it's a little more complicated than that. So let's take a look at this and start by thinking about infinitesimal movements and infinitesimal amounts. An infinitesimal change in time, okay, from the prime frame to the unprime frame is equal to gamma times the original time, okay, plus we have to take into account movement, velocity times dx over c squared. So what we're doing here is we're taking this right here and we're turning it into an infinitesimal amount. All right, so we t prime becomes dt prime and dx becomes dx prime. All right, so we've got time so far. X, going back to the original, okay, we take the derivative, or I should say the infinitesimal dx is equal to gamma times the infinitesimal dx prime, okay, plus in that small little distance that I move, I do that in an infinitesimal amount of time. So this transforms to this equation right here, where my x primes become dx prime, my t primes become dt primes. Okay, now think about what the original definition for velocity is. Our original definition for velocity is dr dt, where r represents the position vector. Okay, how does that change as a function of time? So I go from one frame to the other. For instance, let's say I just want the x velocity. I've got to take this and divide it by this. Okay, so dx dt represents the velocity, okay, the velocity in our frame of reference with respect to what happens over here. Okay, but we also have the same issue with dy. Dy dt is equal to basically dy prime divided by, remember dt, divided by this right here. So here's what the mess looks like after I put everything together. So ux, again, we're not using v here. V represents the velocity of one frame with respect to the other. U represents our velocity within each frame, okay? If we're in frame S, it's U. If we're in frame, S prime, it is UX prime. So here is UX, and we can see we've combined the two equations. Here's UY, okay? Here's UZ, all right? And again, notice that even though my Y and my Z positions don't change under the Lorentz transformation, the Y and Z components of the velocity do change. So again, if we think about our U vector as having a component in the X direction, component in the Y direction, component in the Z direction, when I undergo this transformation, U prime will be UX prime, UY prime, UZ prime, and it will follow these three equations right here. So let's do a practical application right here. I'm going to ignore my Y and my Z direction right here. So it's sort of like one-dimensional motion that we're undergoing. I have a rocket which is observed to go some velocity U prime according to observers on Earth. They are in the primed frame of reference. I'm in my spaceship, okay? My frame of reference is S. It is moving V according to what S prime is. It is moving at a velocity of V toward the Earth and toward the other ship. Now, what will the second ship's velocity be in my frame, okay? And again, remember, we are only interested in this right here. We're not going to worry about a Y component or a Z component. We're just interested in the velocity in my direction, okay? The direction of travel, the direction that the frames are going, right? Obviously, we could come up with a very sophisticated situation where maybe the rocket's going off in some other direction with a Y and a Z component. And of course, that would make the problem a little bit more, well, it wouldn't make it all that much more complicated, but it's just easier to follow what's going on here. So what I have to do is I have to say, all right, I'm in this frame of reference, okay? I'm not worried about, well, it is the same, but opposite. I'm worried about here how my other frame is moving with respect to me, not how I'm moving with respect to it, okay? So the Earth is coming toward me at some velocity V in my frame, okay? That its velocity is positive, it's moving toward me. And this rocket is positive, it's moving toward me. So I'll put these values in here as positive numbers and calculate the new velocity of that rocket in my frame of reference. So let's use numbers here. Let's say, according to the Earth, the red spaceship is traveling at 0.75 times the speed of light. Okay, 3/4 of the speed of light. The Earth is traveling toward me in my frame of reference at 0.5 or 1/2 the speed of light. Okay, conversely, I'm traveling toward it at 1/2 the speed of light. So both of these are coming toward me. I'm going to put positive values in here. Okay, 0.75C and 0.5C. I add them together, and that gives me 1.25C. So in Newtonian physics, in the Galilean, way that we would apply this, we would say, well, the red spaceship is just coming at me at 1.25 times the speed of light, okay? That violates relativity, okay? It doesn't work with relativity. I can't have something that's superluminal. I can't have something traveling faster than the speed of light, okay? Regardless of what science fiction tells you. So notice what happens with my denominator. In my denominator, I have 1 plus the speed of the frame of reference, the speed of the other object divided by c squared. That's going to keep my denominator larger than my numerator. So no matter how fast anything goes, the denominator is always bigger than the numerator. U will always be less than 1 or 1 times the speed of light. So 1.25 over 1.375, that means that in my frame of reference, the red spaceship is traveling 0.91 times the speed of light. Now, it's traveling faster according to my frame than it is according to the Earth's frame, but it still is okay because we are not superluminal. We haven't exceeded the speed of light. Okay, now let me turn the red spaceship around. How do I handle that velocity? Okay. Now, if the speed of the ship is away from me, I will treat that as a negative velocity, just like if the Earth were moving away from me, or I were moving away from the Earth, that would be a negative velocity. So I plug in my negative velocity here, and according to the Earth's frame of reference, it's going away from the Earth at 3/4 the speed of light. All right, so I add these two together, I get negative 0.25, I divide that by my numerator, 0.625, and I get that the red spaceship is receding from me at 0.4, okay? So it's moving away from the Earth faster than it's moving away from me. That makes sense, right? I'm traveling toward it. So as we go from this frame to my frame, we get our new speed. Now, again, this was all lined up. The relative motion of the Earth in my frame of reference were in the X direction. The motion of the red spaceship was also all in the X direction. If there's a Y component or a Z component to this red spaceship, then I need to go back to these equations right here and include those transformations for those components. So if I wanted the speed of the rocket in terms of how it's traveling my frame of reference with respect to me, I would transform the X, the Y, and the Z component, okay? And then I take the magnitude of that vector, ux squared plus uy squared plus uz squared, square root the whole thing, and that would give me my speed, okay? But again, in this case, we tried to keep it simple. So we're only talking about X components with everything. Everything's moving in the X direction.